Hello everyone, my name is Craig and I'm going to be your host for today's webinar called Bringing Formalized Physics-Infused Simulation to MBSE. Today's webinar is going to be delivered by Greg Haun, our lead solutions architect.
All right, Greg, there you go. All right, great. All right, hello everybody. Thank you for joining. So just a brief agenda. So we're going to talk a little bit about why digital engineering and lead through that into modeling simulation, and all the way to talk about a capability we've developed that allows you to simulate these system models, having physics integrated with that as context. So thank you for joining, and let's get started. All right, so talk a little bit about why digital engineering. So given the complexity of modern systems and with the necessity for integrated capabilities with other systems and with, of course, adversarial advancements, our systems are now much more complex. So and in doing so, we find that there are challenges in understanding articulation of user needs. So how do we understand those early concepts? And typically we find ourselves with either static graphical pictures to describe some scenario, and we'll lead into that with some textual requirements that are try to describe a requirement, but again, they kind of lack this semantic formalism that's really needed to get ourselves towards simulation. And ultimately, there's this lack of physics validation as we look at these concepts, and those are some real challenges that we need to address through digital engineering. And really, this has come about because of the struggle as a design matures from a conceptual system model to one that has these systemic interactions where there's external stimuli or physics environment that we need to see the dynamicism of the model and the reaction to that. So invariably, we find ourselves developing separate simulation environments to be able to capture that complexity and that interaction. And unfortunately, at this point, the system model potentially becomes out of sync. So if we were using a language like SysML to describe a model, and we have these other artifacts that we want to integrate, but when we go to simulate, we now have a separate environment, a separate model, and we want to move away from that. So all of this really demands this model-based approach, where the model integrated with these other artifacts becomes the means for simulation. And it really is the actual model that we use across the life cycle. So not just simulated to understand effects from a design perspective, but across the life cycle. So really, having this very formally artifact integrated system model and really leading to this one integrated model that serves all aspects of the life cycle. So there's early design, final design, all the way to operations and looking at different courses of action and sustainment. So really that's the evolving digital thread, right, with the digital twin. But really looking at the fact of that model being the means for simulation with integrated artifacts. All right, so let's take a step back a little bit. Why modeling and simulation? And I think we understand, across the life cycle, the necessity exists at every phase. So at development planning, decision support, looking at new concepts, and going into the early design, we have a need to start simulating some of these things. As we look at the more detailed design, where we have complex C2 interactions, so really looking at, again, the dynamicism, the tipping and queuing, mission effect chains, we need simulation. And as we start to look at vulnerabilities for either exploitation or protection, again, simulation is necessary, because it's one thing to understand the high-level requirements at a high-level design, but until we're actually looking at how the system operates, we're not going to know where those vulnerabilities exist. And really, taking that all the way through to operations, training, and to the point where we want to look at either a course of action development or we're in a battle management scenario. Again, the needs for simulation exist are continual. And really this is precipitated by this thinking adversary. So being able to simulate the model in the context of the thinking adversary across the life cycle. Again, not just early design, but all the way to sustainment. All right, so in doing so, though, in the need for modeling and simulation, we find that challenges exist. So we find that simulations are built to serve one aspect of the life cycle. So I just mentioned many parts of the life cycle earlier. Typically, a simulation tool or environment might be built for each one of those. And I think we need to halt there, right? We need to find a way the system model is the system model. Why can't we use it for simulation across the life cycle? But invariably, we build these separate simulation environments to look at some aspect. And we find that while there are a lot of great tools out there, some very monolithic tools, the tool definitions for these systems become outdated. So doctrine, ConOps, tactics are now outdated. And we need to look at, well, how do we get access to the parts of the model that are deep in the bowels of that tool, and how do we change them? So either, we have to go through code disassembly, comprehension, in order to inject new SME knowledge, and then ensure that that development's done well in code reviews. It takes a lot of time and it's very expensive. So it doesn't always happen. And in fact, a lot of times I find that there are assumptions that are made given how costly it would be to make those changes, where we accept the lack in fidelity in order to integrate these tools together and potentially not look at some of the underlying artifacts. But still, the integration aspect itself is very expensive because they're largely tool to tool. And I think there's an opportunity for us to start thinking tool to knowledge base, right? Is start integrating the tools and concepts against this formal knowledge, and not just tool to tool where it's very difficult to scale. And kind of to that point is, SME knowledge. How can we capture SME knowledge in a more scalable fashion, where instead of bringing the SMEs together to talk about a challenge for a specific system or a simulation environment, we're really leveraging that knowledge more abstractly, where it's easy to look at across many different phases of analysis or simulation. And really this leads us to this aspect of modeling simulation, where you kind of separate some of these components out, really look at modularity of the disciplines. So there's ontological knowledge. There are these descriptive models, so UML, SysML. There are execution methods. So am I doing a design of experiments, or do I actually want to simulate the system, and so on. The analytical artifacts I want to brain in and tie together, as well as other measurement metrics. So again, a way to start looking at how you integrate these together. All right, so let's talk about some goals for modeling simulation. So wouldn't it be nice, if I can document this knowledge in a fashion that's human readable, but also lends itself to machine interpretation execution, and really allowing the subject matter experts to start to vet and describe things graphically without necessarily being burdened with the APIs or scripting interfaces, and really allowing those experts to describe things at an architectural level, again, where I'm not necessarily concerned about the computer science implementation. But then I have others that are interested in, well, how do I formulate the computer science against these underlying principles that are not going to change? Again, I'm forming an environment where my knowledge experts can describe things utilizing these CS nuggets that exist to more formally describe something, but be able to execute them. So ultimately, that knowledge language becomes the hub for integration. So again, instead of integrating tool to tool, I'm integrating tool against a concept, a reusable concept that I can aggregate over and over to understand an evolving system or a concept. So really leading to this one standardized integrated model that I can again use across the life cycle. Okay, so I want to bring this back to MBSE now. And we talked about digital engineering, we talked about the need for modeling simulation and challenges there. Well, within MBSE, the aspect of modeling is definitely there, and simulation is there. And I think that we find, though, that I like to think of the now as, unfortunately, we're at a point where simulation is difficult with these system models. Now, we're able to integrate physics to do trade space exploration, but unfortunately, that design space at first is fine, but as we evolve the design, it becomes overexplored, because as we evolved our design, we now know how the system will behave. And we now need to look at trades that incorporate how the system behaves. So we're not looking at areas of the trade space that are not possible, or are outside of what the process says is possible. And so we find, we're doing requirement validation. We have the parametric integration through parametric diagrams. But again, we're lacking those simulated effects. So unfortunately, it's still an early design, potentially lacking behavioral depth. So lacking state machines, activity diagrams. And unfortunately, maybe just being a graphical form of documentation. While there's value in graphical documentation, there's a lot more value to be had from these system modeling languages. So the future, I think, where I focused a lot of energy is the ability to simulate these behavior constrained models by integrating physics environments to be able to look across the life cycle. So instead of building different simulation environments, use the model as a means for simulation. So I now can start to develop a detailed model that has the depth of executable behaviors. And that detailed model with the behaviors can now be integrated with a synthetic mission environment where I can ask questions that are relative to those behaviors. So now I can start, that model can start to live and breathe in that synthetic environment. And really moving to this digital twin where it behaves and operates as the system at enough detail to answer the challenges across the life cycle, and really moving to where I can answer operational questions with that exact same model that I used to design. Okay, so I'm going to talk about why these descriptive languages, so UML, SysML, and so on. But before I go through the slide in detail, I want to describe a customer interaction that I've had that I think is very interesting and reinforces some of these concepts. So this customer interaction that this customer I was working with, the group didn't have familiarity with UML or SysML, MBSE. Those terms did not mean anything. But the challenges were the same. They found themselves developing PowerPoint state machines. So again, if I look at the graphical in nature aspect that this slide states, so the graphical aspect of describing a concept or a system is very powerful. In fact, this customer was using PowerPoint with graphical state machines to try to vet and talk about a problem and how a system behaves. Unfortunately, at that point, though, they'd have to hand those PowerPoints off to a group of developers that could take that architectural representation and try to turn it into code so they could exercise the system. Now, there's vulnerability in did they get it right? Did they interpret it correctly? And 6 months later, they might have it. How can I ensure that it did exactly what my PowerPoints had shown? If I need to make a change, how do I do that? But again, so what we did was we brought the aspect of executable UML to them that allowed them to look at, well, I can graphically vet my systems and concepts. I have that semantic formalism. I can become executable. So I can describe the structural aspects of a system. I can describe behavior of a system. So all of the aspects, these descriptive languages brain brought the value this community required. And I think, what I really like about that story is that part of the vision for these descriptive languages, and specifically SysML in the design of a system is, well, there's no reason why I can't use that design as an operational model. And in essence, that's what we were doing for this customer. We skipped the design phase, but we showed them how you could use these languages to describe a system and concept and hit go and execute directly off of the graphical representation. So I just wanted to introduce that concept. I think it's very powerful, and I think the rest of this presentation is really going to focus on the ability to simulate those system models with integrated physics. Okay, so but before we do that, we need this physics playground. So the system model will describe the what and the how, and we need a where, and we need those constraints of the playground to place that model within. So this slide is going to show some of the analysis capabilities that a tool like Systems Toolkit, AGI SDK, would bring to bear. And if you think of the multi-domain capabilities and the analysis that you see on the screen, those are all areas of questions that my system model can live within and ask of. So again, I can have a very detailed system model with a very rich behavior, and brought in this physics playground can start to interact and tip and cue based on those questions that the behaviors define to really have a fully breathing model in my synthetic environment and understand what if type cases and so on as I move to detailed design all the way to operations and sustainment. All right, so I want to take some time to describe an early example of this simulation of these descriptive language and the physics environment. So this example I'm going to describe is really more, the interest is, does it make sense to integrate a physics mission environment with a behavior-rich set of models and let them play out? And it definitely does. It does make sense. So this example is, think of an autonomous air system where the aspect of that vehicle is predominantly purely sensor and software driven, and that's relative to the environment and other players in the environment. So as I build that design, before I really build the system, I'd like to assess that design in a synthetic environment. And I don't want to go off and build a separate simulation environment just to assess the design, because as I change the design, I do ensure that the simulation environment is up to date. I actually want to use the system model as the means for simulation and just bring the synthetic physics environment. It is physics, it's not changing. The system is what I want the design to be, and see how it plays out. So again, this is a very simple design. The only intent is to say, does it make sense to integrate these two? And yes, it does. So we're looking at a state machine here for, let's say, a blue aircraft. And again, it's very simple. There's 4 basic states. I'm either flying mission, I am avoiding red, I'm flying home, or I'm holding. And the transitions define the criteria that causes me to transition to that state, as well as the action to take. And take notice of the upper right hand corner. There is coming out of avoiding red, there's a fuel to home reached, causing me to go to flying home. And this is saying, well, if you're currently avoiding red and you have just enough fuel to return home, I want you to fly home. And again, the value of this graphical approach is that I can say, well, do I really want that behavior? Is that really what I'm after? Well, let me go simulate it and see how it plays out, and so on, right? But the benefit is that I can just delete that transition graphically and run it again, and have to write any other code to go assess the design. All right, so we also have another player. We have a red system. It has 3 basic states, either holding, following blue, or flying home red. And we're going to put these 2 models, and there is actually a sub-machine. We're not going to dive into it on how track processing is done, but let's look at a play out of this scenario. So we have these 2 systems, and this is in a tool called Magic Draw, and we have a little picture-in-picture view of SDK providing that synthetic environment. And one thing to take note of is in SDK, you typically build out your whole mission workflow. You know how it's going to play out. You build out the whole flow and you do your analysis. What's really nice about this is that SDK is providing that physics playground. I can play the models out, and then I can do analysis against the play out. So none of the initial state, or none of the playout's not prescribed. The initial locations and state of the models is defined, and then I can play this out according to the behaviors. So let me play this video. So, and again, so purely being driven by the state machines here. So initially, red sees blue, and now red just transitioned to following blue. Now blue hasn't seen red given its sensor profile. So I haven't actually got into avoiding red. I'm still in flying mission. As soon as SDK can answer that, oh, you now see red in your rear looking sensor, well, I'm going to go avoid. And avoid was simply 90 degrees opposite incoming threat. Very simple. We're proving a point here. So red is still following blue. At some point, red will just have enough fuel to return home, and red will turn home because we told it to do that. The behavior in the state machine says that when you just have enough fuel to reach home, you're going to return home. Desired or not, we can tweak those state machines and have a different behavior and see how it plays out. We could have had an engagement state and so on. But again, the value here was we were proving the point of where SDK can provide the physics playground. We can ask it questions relative to the behaviors in our state machines to see how something would play out. So again, very valuable. But I want to back up just 2 slides and point out one thing. So we'll look at this blue state machine. You notice that the transitions have text in them, as I mentioned, so the events, guards, and actions. And a human can read them, and I can pretty much understand what I expect to happen. But it's not formal enough for the machine to interpret it. And that's what we're going to dive into next, is that we've shown the value of integrating these together. We're going to look now at how we can create a very formalized method to describe the events and the actions that you take to build a very formal way to describe a very detailed system. All right, let me jump forward. Okay, so I'm going to introduce this concept of this formalized knowledge language. And I talked about this early in the presentation about this need for formalized knowledge as a means for integration. And, whatever term you like, ontology, domain language, information model, but really the concept of being able to describe things at a abstract to specific level that I can use for describing a system, asking questions, and ultimately as a means for integration. So let's go into a little more depth. What do I mean by this ontology? So think of it as this hierarchical dimensional arrangement of knowledge. And I'm describing things from a physics perspective all the way to a process interaction. And it's described at an abstract all the way to a detailed, whatever's necessary to look at your problem statement. But again, instead of just describing my problem statement, I'm describing things at a more abstract level as well, because the next time I want to ask a similar type of question, I want to have an environment available where I can go ask those questions without bringing SMEs in the room again, without doing computer science implementation all over again. So this also becomes, think of it as a standardized semantic standardization for integration. So all of these other codes that I have in my environment, other algorithms that subject matter experts have developed, well, it becomes almost an interface control description, or think of it as a very formal means to access that model in the future, so that I can get access to it and I can execute and I can describe it over and over and over, instead of just thinking of it from that one system's perspective. All right, so let's look at what does it mean to use this now. I think that'll help describe it. But I'm going to give a very simple example of I call this simple ontology. This is more for fun. And I'm going to zoom in a little bit here. So imagine I have a concept of a human and an enforcer. And I say, well, I have this police officer, and a police officer, well, he's going to inherit from a human. He's going to have needs that a human has, so the attributes and capabilities and behaviors, if I had them defined. So that's the other key aspect, is that these ontologies are behavior rich. But the police officer also inherits from enforcer, so that there's a contract there. I've said that an enforcer can enforce, and he always has an enforcement apparatus. So I can reason that this police officer is going to have an enforcement apparatus as well. And in fact, in this case, I'm going to say it's a gun is his enforcement apparatus. But I now can start to ask questions about this police officer. I can say that, well, I can tell him to go enforce because I know he's going to be able to do that. But at the same time, I could have a UAV that is also an enforcer, and he's a kinetic object, which also a human inherits from. So again, I have similar needs, but I may want to choose to redefine those. So instead of having food, I have fuel. But again, so this becomes that common background that I can describe a domain or different elements that I can use as a language to describe a system. So I'm going to show you an example of what it means to use that ontology. But before I do that, I'm going to show you some visual charts, just visual magnitude here. So this is an early version of what we call our core ontology. So again, you're not going to be able to read anything, but it's more for visual magnitude. And we have concepts of activities, of concept, and of entity. And we can describe all types of things we might want to look at. So perceptions of things, what does it mean to be a velocity, all sorts of things. So more core level elements. We also have this space domain ontology that allows us to talk, again, just a visual chart here, allows us to talk about all sorts of space things. Am I space chasing? There's different types of transfers I do in space. I do in rendezvous prox ops, so on. But I can describe all of those things very formally as a formal knowledge basis, but again, very behavior rich. Okay, so here's a small snippet of that space ontology. I'm going to zoom in a little bit. Oops. We have this concept of a space entity. We have a space vehicle, of space chasing, and we also have a space chasing response. And you notice that we have state machines on some of these elements. Again, it's a very behavior-rich ontology. There are other elements that you do not see where we have more specific aspects of the system. So we have a very generic GNC. We have other more specific GNCs. But again, this describes all of the relationships that exist amongst the different concepts, things, activities that can be performed, as well as the methods that they might be performed. So there may be very specific methods that you do a transfer in space. Well, we would, like a Haun transfer, if you're familiar with the term, or a bioelliptic transfer. The benefit is we describe those in state machine form where I don't have to be an expert. The knowledge has been captured for how you do a Haun transfer. So if I want to go, hey, go execute Haun transfer, it can do that for me. So it becomes that knowledge construct. Okay, so let me back out of this and show you, well, how do I use some of that ontology as I'm describing a behavior? So this is a small snippet from a state machine on a single-threaded GNC design. And you now notice that what's on the transitions is it's still human readable, but it's now going to be machine interpretable and executable for simulation. And you notice that spacecraft has sight to, and I'm asking it has sight to its GNC station for at least so much time. Well, again, the benefit of the ontology is that because a spacecraft ultimately inherits from an entity class object, he can ask that object can ask has sight to. Well, has sight to produces in this case a duration of validity. So because that's a duration, I can ask for at least against that. So again, I can build up these very complex statements from the ontologies for execution, but I'm not going to write any additional code, and I'll describe how that works a little bit after this few set of slides. But then I also have the activity, right? I'm saying, well, I want you to go update your remote perceptions, and that's captured in either some more detailed behavior or an activity diagram. So again, very formal. Okay, so I want to show you, I mentioned the word delegate, or I mentioned, execute and the other tool that's going to back that. So I want to describe what do I mean by that. So I also talked about the ontology as a means for integration of tools. So I'm going to show you an example of that. So if you notice that this snippet, I have entity and I have physical entity, and spacecraft would have been way down below. But if I look at has sight to on entity, well, has sight to can be asked to any other entity. And then if I look at physical entity, I have an is lit by. Is lit by has to be asked of a light source object. So it's very formal. But I'm going to integrate my other tools against the ontology here as delegates. So I'm going to focus us back up to the has sight to. And you can imagine if I'm using has sight to as a statement on my machines, well, what happens? So this is a snippet of code using the STK object model to answer has sight to. And I could choose to, if I wanted to build a simulation and I wanted to answer has sight to in the context that I've described, I'd have to write this code each time or pull this nugget out. But with the ontology, I get hey, here's the contract that I say that you're going to have to adhere to. And this delegate that we call it here has to adhere to that contract or what I've said that object can do. And this becomes the CS aspect of the implementation I described earlier, where now I can use has sight to on my state machines and not have to write this code each time to find out what did I mean. So with that early example with the autonomous air vehicle, the code was specifically written against the transition itself. Now we're going to describe state machines where this code has been written against those delegates, and the delegates will be used in the state machines. In fact, they'll be interpreted and executed behind the scenes for us. Okay, so what do I mean by that? So, and I mentioned that we built this capability that will interpret those statements on the fly. So that small snippet earlier of the state machine, where it was now using the ontology, our engine will interpret those statements on the fly, and we'll do a little bit more. We're then going to be producing events from those interpretations and then commanding actions. And this is how we would do that. So you can imagine if searching is the current state inside of aperture open, another state inside of a larger state machine for an optical camera. And in fact, I could have much more than just one state machine. With the earlier example of the red and blue UAV, I had two state machines. But I may have state machines for an optical camera, for the system that it sits on, for state machines for the doctrine, state machines for another vehicle. Again, there's many state machines running. But in this narrow case, I'm going to be looking at searching. Say, well, great. In order to look at what state I would transition into, there's these four basic transitions I'm going to be analyzing. And in doing so, there's three that are directly coming out of searching and one coming out of aperture open because searching is contained in that state. And all of these statements are built up from that ontology so that on the fly, the engine can interpret those statements, run the delegates to the tool of choice, and generate an event. And so for all four of those transitions, I will generate an event at some point in the future. And based on that event, I may need to run forward more from discrete time in nature or not, but we'll determine the next event of interest. We'll fire that transition, which does two things. If there's an action on that transition, like in this case, if you look at the one on the right, the one coming out of aperture open, maybe we're going to go into sun protect mode. So we would go into another state, or if I was coming out of searching, let's say going into tracking. Again, I transition into that state, but I'm also making a change into my different integrated environments. So by saying sun protect or track, I caused a change in my integrated physics environments. So that when I'm in my new state, I have new transitions, new questions to ask, but my physics environments or my integrated environments are also different. So again, you can see how this plays out over time. And in fact, it can even become much more complex. So the environment that we built, again, it's not just that I can integrate with a physics environment, but I may have multiple physics environments backing an aspect of a system. So I may have two system designs. Maybe one is adversarial in nature, and the other is my design system. And I've decided that, well, I want my adversary system to be modeled by this external simulation environment that I have. But I want my design system to be modeled by these state machines. Well, the engine that we built can handle those just as well. So it really allows you to marry not just the physics modeling environments, but other simulations can be tied in as well. So it's very powerful. And I can describe some of those use cases in more detail a little bit later. All right, so I want to talk about a specific implementation where we use this environment with these ontologies. So the work that I was doing is classified in nature, and I had there's one other benefit of the ontologies I didn't mention, but I'll mention it now. And we looked at all these different challenging types of use cases. I mentioned we have perceptions, so I can target things on perceptions and so on. And let me bring one point to bear here. So if you're familiar with STK, and you notice in our ontology we had GNCs, but there's not really a concept of a GNC or of a perception of a vehicle or of an activity in STK. Well, that's okay, because the ontology allows us to leverage the capabilities of a tool with those delegates, and it doesn't really matter what the implementation is. So if I'm using a targeter in STK as a numerical integrator for our GNC, fine. If I'm using a perception of an object as a real object in STK, fine, because from a physics standpoint, I'm okay with that. So again, I can leverage the best of breed capabilities of a tool. The other value, though, here is that the core ontology was not classified in nature. We had other ontologies that were, and we had all these interesting use cases that we were looking at. And I realized that, well, I didn't have an unclassified demonstration that I could provide. Well, back to the points earlier that I mentioned about once the CS, the computer science work is done against those delegates, I can build up all types of other interesting cases. Well, that's what we did. We built up a shuttle ISS example out of the same ontology to be able to look at shuttle ISS rendezvous prox ops and docking. And again, I would say 90% of the ontology is unclassified in nature. And it's really the aggregation of those elements that allows you to describe other interesting things. So again, very powerful in looking at other use cases that are similar in domain or other abstractions where I don't have to go off and develop a whole another simulation from scratch. So let's look at an example of that. So here's a video of that kind of use case, and I'm going to describe it in a little bit of detail here. So this is still somewhat simple, and we've done much more complex simulations, but it's very, very powerful. So in the lower right, you see a picture-in-picture of STK, and I have a shuttle and an ISS. And again, the initial states of those vehicles is known, but in STK, nothing else is prescribed. Right? I've used the instance diagrams to populate my system representations, but it's the execution of the state machines and the play out from a simulation standpoint that's going to allow me to see where the states play out in STK to where I can ask other analysis questions. Directly above the picture-in-picture, you see a state machine for an optical camera. To the left of the picture-in-picture, you see a ConOps for what we call a shuttle stable orbit method. So the other interesting thing here is that there are different methods for the space shuttle to do an RPO over the years. We chose one called stable orbit. We built up state machines with some other activity diagrams that we use in the ontology that define that method, very formal, that we're going to execute from. And then above that, we have a very simple GNC, a single-threaded GNC that we're going to use to represent the shuttle and allow us to play out this use case. So I'm going to begin the video. Just play in mind that it's all of these interacting state machines by setting flags or asking questions of other systems that cause this play out. One other thing I want to mention.
Before Greg starts this video, I do want to mention that over GoToWebinar, the video may seem choppy. It is due to limitations in GoToWebinar, but we're going to send the slide deck out after in a follow-up, so you'll be able to watch the video streaming without any interruptions. Sorry, Greg.
Thanks, Greg. I did want to mention one other thing. You're going to see where you have shuttle RPOD, the ConOps. That screen's going to flash out at some point when we go into what we call an operation or a guidance. And this is to what I mentioned earlier about a Hohmann transfer, a Lambert transfer, a bioelliptic transfer. I don't have to be an expert for what it means to perform those because we have state machines that determine how those are performed. We also have the state machines in the GNC that are going to determine when our perception of our vehicle is off from what we deem acceptable to where we have to go do a recompute. And you'll see some of that happening. So I'm going to play this now. So initially, ISS and shuttle. In this use case, the ISS is not going to do anything. It's cooperative in nature. But we noticed that we actually just started through a guidance. And we're coming into where we can go into closed navigation now. So our optical camera actually just switched to tracking. Again, that was given the physics constraints, allowed our model to progress, which changed the behavior in SDK. Our GNC just went and got a remote update from the ground, which caused him to do a recompute on one of the guidances. We're now actually going to go into another near rendezvous where we're coming in closer to the ISS. And then we'll go into an approach. So we're in, again, this is all modeled from a different, we're using finite modeling. Finite burn modeling may not be important to you, but the value is we can capture that in the ontology. So again, it's very formal. So the shuttle's coming in again to the ISS. We're going to do another approach. So all of these state machines are interacting together because when my GNC can't go to closed loop navigation till the optical camera's been in track mode. And you can define other constraints for, there's hysteresis for when I go from tracking to searching. Again, it's very formalized, it's all captured in the model. So I described earlier that we had integrated other more elaborate cases. So we have examples of this where the GNC has like 8 different state machines. We have examples where there are many, I will call shuttle objects doing RPO. And, we have examples where I said this is all perception driven. It's not perception driven because that's how we developed all of our code. It's because that's what the ontology allowed us to choose from. So, and the ontology isn't necessarily something that, hey, this is all that you can use. The engine allows you to interpret those statements on the fly. So if you build your own ontology, your own delegates, we'll interpret those statements and run them. So again, it's not locked to that ontology. It's very flexible. So I'll take a little bit of time and just talk about, well, you talked about this engine. What do you mean by this engine? So this engine, and this is comprised of a few elements, right? There's this ontology or knowledge information layer. And I've shown you some examples of that. There's the interpretation and reasoning engine that allows us to interpret those statements on the fly. And then there's the environment that allows us to evaluate those events and process the activities. Those are all part of what we call this UFOs, Unifying Framework for Orchestration and Simulation. At the same time, we're looking at bringing this type of execution to SDK as well. So you can imagine an SDK user that's not trying to do model-based system engineering, but they simply wanted to start to describe some behaviors for their system or for what they're building in SDK. You could now do that in SDK, satisfying some of those needs that I described earlier, where I may not be a model-based system engineering user, but the needs are the same. The value of simulating a model built in one of these descriptive languages where it's very formal, integrating my artifacts, one model for simulation, very powerful, and I believe that's where we need to move to. So I think we'll open it up to questions now. That's the extent of my part of the presentation.
Do you want to take a look at the
Sure.
questions?
Sure.
In the GoToWebinar window, there is a questions panel. Please send those questions in. We do have a few more minutes. Greg's going to jump on the microphone here and asks or answers some of the questions that he sees. Let me pull this panel up for you, Greg.
Sure.
Okay, good. And then if we don't get to some of these questions that you ask, have no fear. We will have a member of our team follow up with you specifically. So, all right, there you go, Greg.
All right, great. All right, so thanks for the questions. I wanted to focus on a few areas and just to clarify some points. A very good question. So one is, what is SDK doing in these? And it looks like only Viz. And I wanted to talk about that. So I mentioned that physics playground. SDK is the physics environment that the models live within. So if I have state machines that describe questions like when I can see the sun, go do this, SDK is going to be answering those questions. Well, the questions are being asked, so the engine is asking them from a discrete event perspective. So we're going to ask those questions, find out when those things are true, and then determine what does our system do next, and so on, right? So then if we change something in the environment, like we maneuver, and we're in a new state, and there's new questions to ask, those answers are going to be different, which causes the system to behave differently. So it's very much SDK is that physics environment. But I want to dive into some other questions. So it talks about, this is done in Magic Draw, and I want to talk about, if you're familiar with Magic Draw, if you're familiar with, there's a module called CST, Cameo Simulation Toolkit. And why is this different than that? And how is it similar? There's also some questions on Model Center. How is this different? How is it similar? So one of the things, so with CST, it allows you to do, Cameo Simulation Toolkit allows you to do simulation, but it's very discrete time in nature, meaning that the condition has to exist now for it to be true. And we wanted this to work very discrete event in nature, which is typically how you see a lot of state machines where they really add their value. And being discrete event in nature, we can take events that in a tool like SDK we produced in the future, so we can jump to things of interest. We may have other tools that are integrated with the environment that are more discrete time in nature, where we have to advance them a step at a time. But the engine that we built, the UFOs, is aware of those through the delegates to know how to ask those questions. But it's very powerful in looking at simulation where I have maybe 50 different objects, where each of one of those may have 10 different state machines, and I don't want to wait hours for the simulation to complete. And having an advantage of physics environments where I can determine those things up front. So that's one fundamental difference between CST. Another difference with Model Center is that Model Center allows you to capture really the glue code between them and also the ability to do trades. But it's not going to give you the ability to do simulation. So again, when I say simulation, I mean using that system model, those state machines, those activity diagrams, as the means for the rules for simulation, where and then so the linkage to these other tools is simply through the ontology. So there is value in being able to do those trades, but I would like to do those trades in the context of a simulation. Let me look through. So other questions. Sorry. Okay. So the integration, there's some integration questions. So we built some of those ontologies to support the activities that we were looking at for, space related or even the core ontology. And we built those delegates that back the ontology. The ontology, as I mentioned, it was just built in UML. Again, very behavior rich. You could choose to build your own ontology and your own delegates. So, currently the ontology is designed to be this open thing that can be provided, but there's a freedom to develop your own and back it your own. The engine that we built will process it the same. So the engine, again, it works. It will work in place with CST, but it's much more powerful than CST. And Model Center will allow you to ask those parametric type questions through those linkages, but you're not going to actually be able to simulate the model in the context of integrated physics environments. So like in those cases where you saw here where I had an aircraft that was interacting with the environment and you saw the play out of it, or in the case of the rendezvous proxops and docking use case where given how the space shuttle's GNC operated, how the optical camera operated, the rules for those different transfers, how that simulation played out. It was the coupling of those state machines of the system model with the physics environment. And as I had mentioned, other simulation environments as well. So I will mention one other thing. So there was one slide that I went to. In fact, let me go back. And you noticed that there was a space chasing response state machine. And there are some avoidance tactics. So what you didn't see in this case was the ISS was cooperative in nature. But I may have state machines that define, well, what does it mean to be a response, and how do I determine my response? I may determine that something's uncooperative in nature and decide to go down a whole nother order of operations or guidances that I can take based on the rules that have been defined. So again, it's very discrete event behavioral nature. System, okay. Okay, so there's a question, how does STK connect to the state machine? So maybe let me address that again. So the state machines, in fact, let me move down to a state machine. So here's a snippet of a state machine. Here's that ontological statements on the state machine. I mentioned that has site to. So in this example, the engine that we built would interpret those statements on the fly, determine that, oh, well, I need to run the delegate for has site to. Well, the has site to delegate is a delegate that's in STK. So I will have populated the vehicles in STK from an instance diagram. And I can now ask those questions has site to. And we will get back the times when that is true. And then we're going to pass that to for at least and be able to evaluate for at least. So it's through that mechanism that we will ask the questions to STK or any other tool that's been integrated. And ultimately, as I had shown in this, I'm going to jump down slides again, in this slide, ultimately we're generating events. We want to know a time or set of time when something becomes true. We also want to know the guard space, so a Boolean space that's true, and then rack and stack them all and determine the event to fire, moves the simulation forward. That's how the integration works. Again, the delegates are the integration that's performed against the ontology. So it does not require code to be written against the transition other than the ontology statements that you see on the transition. So I gave a demonstration at a No Magic Symposium once where I changed a statement on a state machine and hit go again. I had some hysteresis for a sensor and it allowed it to go from tracking to searching with some other delays, some hysteresis. I didn't have to go write anything in the STK object model. I simply used the ontology to change the statements on the transition and hit go. That's how the integration is done, and that's the value of that type of integration. Again, the integrations against the ontology. Okay. So I think so. There are a lot of other questions, and I think it may be better. I'm trying to track them all. It may be better. Actually, let me see if there's any that relate to all. If we'll take some of these, and we can potentially have some offline discussions to get into more detail. And if you want, so again, I mentioned that UFOs environment. That's really the environment that is performing that interpretation and execution, and the ability to link in these other tools. And if we need to, we can go into more detail on that at a later time, I think. Good. All right. Well, I appreciate your time today. Thank you very much. I hope to have some other interactions. We can answer some more of these questions and provide some better clarification. But very exciting being able to present this to all of you. Thank you again.
All right. Again, thanks, everyone. We are going to follow up with those questions that we have there individually. But if you have any further questions, please email us at info@agi.com. And again, we want to thank you for joining the webinar. And for those questions that we didn't get to, we will answer those individually when we sign off. We also did record this, so we will have a recording of this sent out in a follow-up email. So do not worry. We'll have all kinds of resources available in that follow-up email. So Again, thanks for attending, and we hope to see you at an upcoming webinar. Thanks.